So, if your valuation, so imagine that that third agent, right, if his valuation was not the highest, I do not want him to be the winner. So, even under that situation, that agent, so if his type is or valuation is low, then still this should hold. It is like saying if you are, so the mechanism is telling you or the F is telling you that you play this second price auction. It is so you as an agent I, whether your valuation is high, then you should reveal that high value truthfully. If your valuation is low, you should also reveal that valuation truthfully. So, if you are low valued, you should not bid high, try to become the winner, because that is getting penalized according to the mechanism. So, this is why for the same agent, for every defined theta I have to satisfy this. Yeah, any other questions? So, we will now get into that. So, at this point, this F, if you think about the auction problem, it is a combination of the allocation as well as the payment. We will very soon bifurcate these two things, and that is exactly where we are going to do. So, mechanism design with transfers. Usually, I cover it in the way that mechanism design and then those voting and other stuff, and then come to mechanism with transfers, because it gives you a kind of a panoramic view of how we actually ended up with transfers, how monetary transfer can make life easier. But because we are starting from here, we will just use this particular setup. Let us imagine this one. Okay. So, and just to make sure that it is different, so there is slight change in the notation. So, now we are actually interested only in the allocation problem. So, which item or which of this outcome is taken, and that is given by some capital F. There is a reason why I have chosen the capital F. So, suppose this is my objective, because in transfers, in mechanism design with transfers, we will be mostly talking about something else for which we will use the lowercase f. So, this is the same as the previous social choice function, just imagine that small f has now become capital F. This is my objective. So, space of all outcomes here has two components. So, in the mechanism with transfers, we have two components. One component is the allocation component, that allocation or choice of an alternative. Let us say in the public project, my allocation or decision is that I will build a bridge, right. So, that is the allocation part, and then I can tax each of these individuals, so different amounts depending on how they have reported their theta i's, which is the part of the payment part of this outcome. So, you can, I think we have discussed that in the example before. I am just using a different. So, you can think of that as p. So, the same p has now become pi. So, each of these are some real numbers, each of these real numbers are the payments that I am charging to that particular agent, and this is the allocation. Now, so what are the allocations? So, this is the example that you have the choice in the public project problem, that you can build a bridge, park, or a museum. So, your allocations can be one of these outcomes. In fact, you can also take a later on tomorrow when we discuss about this, we can actually have a mixture or a probabilistic choice between these two things, but for today let us assume this is a deterministic choice, either you choose a park or a bridge, not a mixture. Now, it could be an allocation of a divisible good. Okay, so, like a shared spectrum. So, now each of these numbers, individual numbers, are some real numbers between 0 and 1, and when you take the entire space. So, it is like a share of the entire pie, that should be exactly equal to 1. In fact, you can also add a 0 here by saying that that part of the spectrum or the divisible resource was not allocated. That entire summation should be exactly equal to 1. So, the fraction of the resource that I gets, this could also be a valid allocation. Okay. For each of those allocations, you have a value. Okay, so, the other example is single indivisible object allocation. This is what we have seen already. These numbers can be either 0, 1 indicator variables, whether you win or do not win, and of course, the sum should be less than equal to 1. Partitioning indivisible objects. So, this will also show up in some cases when we talk about combinatorial allocation. So, think about I have a set of objects to be given, chairs, tables, indivisible objects, computer, etc. And you can think of each of this as so allocation. So, the set of allocations is some partition of this set of S. Okay. So, each of this is A is a subset of S, and they are disjoint, and together they might not even make the entire set. So, that means some of the objects are unallocated. So, I have not put that union of A I to be equal to S, might not be the case. So, all these things are set of all possible allocations. Now, what we are going to assume is that this type of an agent. So, and we will assign how this type is designed. This is a private information, and how these agents benefit from that allocation is defined using a valuation function. This is a setup which is very specific to mechanism design with transfers. So, we will introduce. So, all these highlighted different colored things are some keywords which we will be using later. So, valuation function. So, what does that mean? If you take a specific allocation, the set of all these examples that I have given, a specific A. So, the set of all possible A's, small a's, are denoted by capital A. I think I have missed that part, but anyway. So, you see that set, you pick one allocation from that, and depending on what your type is, and we are using independent private values, you have a real number associated with it. So, think about that public project, that if bridge is built, so let us say this. So, I am talking about agent 1. Okay. So, V 1 when its type is theta, which is 190 and 20, if the allocation, the A happens to be bridge, then his valuation is 100. If if park is built, 90, and so on. Okay. Yeah. So, here so I am reusing the same example, because there is payment also associated. So, this is just the valuation. I have not come to the payment part that will alter your utility, right. So, I mean, just to jump ahead of your time, but this will mean that the valuation is given by that number. If I charge you, if I tax you, then that tax money is deducted from your utility. So, you will valuate 90 minus the payment that you have been asked to pay. Okay. So, yeah. So, right. So, in the public park, the public project example, if your type, so suppose your type is theta I, you are an environmentalist. So, maybe between bridge and park, you will have a higher valuation for park rather than bridge, because that is environmental friendly. But if you change to something like, so that is why this set of theta I is important. You may have different types of theta I's. If you happen to be an environmentalist, then your valuations could be different. If you are a businessman, then possibly a bridge is better for you. Okay. The second part of which is unlike other domains, we have an instrument which is the money, which is payment or transfers. So, what we can do is we can decide certain allocations, and then I can transfer this happiness using this instrument called money. That is essentially why it is this called the mechanism design with transfer. So, I can transfer happiness between agents using money. So, it is something like what does the money give you? I mean, it is just giving you, transferring your utility. In the absence of money, whatever you get it, you cannot really transfer it. But now, with this help of this money, I can actually give you maybe a worse outcome, which is not so valuable for you, but I can compensate you with money. While somebody who is getting a better outcome, I can tax that person some amount of money, so that the utility still sort of remains what I want it to be. Okay. That is the sort of intuition behind money. So, payments are all real numbers, and use this payment vector. So as I said that this x in this mechanism with transfers will be a tuple of two things. One is the allocation which looks like the previous, and some payments, and that is given by this special form which is called the quasi-linear form. Why is it quasi-linear? You see that there are two components in your decision variable or the x, the outcome. The utility is linear in one of them, the second component, but possibly non-linear in the second component, the first component, right. So, the valuation could be anything. So, like we said, if your theta is environmentalist, then depending on which action you take, your valuation could be different minus the payment that you make. So, this is no longer an utility anymore. So, this is just the valuation. If I charge you certain amount of money, the net thing will be the total utility. So, yeah, so the quasi-linear terms come from what is the outcome. So, this is our x, right. So, our x which is my outcome. So, I am choosing a specific outcome. I prefer one x from another x prime, right. So, here I have these two components, one is this allocation part, one is the payment part, and it is quasi-linear because your the utility is linear in the second component. So, how much I charge you, that is exactly linear in that payment. In this case, I have assumed that it is also linear in the first case, but it does not necessarily have to be. It could be something like a, so if I give a bundle of objects, maybe you have a completely different valuation for one bundle versus another bundle. So, there is no way I can associate a linearity with that. Okay, so we will be only, yeah, was there any question? So, we will be only dealing with this quasi-linear setup. So, imagine this as I mean if you just want to remember a public project where one of this the allocation is one of the decisions of the planner, maybe the municipal corporation, and how much you have been taxed, right. So, and that difference is your net utility. Okay. So, this is the quasi-linear domain. Let us skip this part, it is not relevant for us. Why it is a domain restriction? This is from the slides of my course. Now, what is quasi-linear preferences? So, now we are trying to get back to the mechanism, right. So, now I can actually say that I have some function which I want to satisfy for the allocation, and there are certain payments associated with every agent. So, there are two components into it. So, as you see that my social choice function, in this case we have used the social choice function to be capital F. So, I have this capital F which is mapping my capital theta, which is like the Cartesian product of all these individual sets up to capital theta n, to the outcome set, and we know that these outcomes look like the following. We have an allocation part and one payment part. So, I need this function to map from the type set to some allocation and payment. It is something like saying that, so if you want to say that that single object allocation, I want to get to some allocation where whoever has the highest valuation for that item, I give the item to that agent, and some payment. We have not discussed about this. So, this the first component. So, you can decompose this part into two different parts. So, because it has A and P, so you can think of that this function is doing two different stuff. So, this capital theta, which is the Cartesian product, one function is taking it to the space of allocations, which is the set A, and that function is F, and another function which is taking it to the set of real numbers. So, let us say r to the n, because I will have to assign some payments for each of these agents. So, therefore, it is a collection of n different functions. Each of these things are treated separately. So, there is a component which is the allocation rule component. Just think about this in this way, and there is a payment function component which is, so together this f and p will give you the capital F. That is the reason I have used a different notation here, because we will be using this F which is the allocation function, and we will just try to find if there exists some payment which can satisfy this objective in some dominant strategy incentive compatible way. Okay. So, that is the objective. Okay. So, that is the, so F you can think of as is something like one F function and collection of P functions, and this is the target. Now, from now onwards I will forget about this capital F, I will only deal with this lowercase f and the payments, because you will have to finally decide how much which allocation or which of these alternatives you are picking. If you are doing public projects, which of these public projects you should pick, and how much you should tax each of these agents, how much payments you should charge. Now, let us look at both these two things, some allocation rules, some payment rules, just to get familiar. So, one could be a very there could be some very dumb rule which is just a constant rule. I do not even look at anybody's type, I just take a constant decision, the way the government does things, do not ask for anybody else's preference, just do it. There can be a very strange rule which is a dictatorial rule. This might also be relevant in some cases. So, you designate somebody as a dictator, and whichever outcome, whichever allocation maximizes that agent's valuation, you just pick that one. So, see this notation that there is this dictator and this is his type, and whenever we are looking at the valuation of that dictator, I am just picking that one which maximizes his valuation. No payment required. Yeah, so that is a good interesting rule. We will look at this later as well. The third one, we have already seen it. So, just remember this terminology, the allocatively efficient rule, also known in the economics social choice literature as utilitarian rule. Why is it utilitarian? Because you are looking at the aggregate population. So, what it is trying to do is it is summing the valuation of all the agents, as if the society, as a society, the sum of the happiness is maximized at this outcome A, right. You can always complain about this rule and all the complaints are well taken, because there could be a situation one person is getting very happy and somebody is not getting any valuation at all, right. Still it maximizes the, so there is a sort of a discrepancy in how good or bad this is for each of these agents, but it is not taking care of that, it is just summing everything up, and whichever maximizes, that is the one that it is picking. So, this is allocatively efficient. And a little generalized version of this is where I can assign different weights to different agents. So, it is almost similar to this previous one. The only change is now I have put different weights for different agents and some translation to the allocation. So, maybe the mechanism designer wants to push certain allocations. So, it is pushing this those allocations with different kappa functions, and for different agents it has weightages. So, in some sense it is affinely transforming the allocation to something else and trying to maximize that affine sum, and that is why it is, the name is also affine maximizer rule. You can define many such things. So, one interesting one observation to make is when you have all these weights to be same and kappa to be exactly equal to 0, then you get back this one. So, this is fairly simple to observe. And when you have this only one specific mass to be maximum, so you have exactly 1 and everything else 0, that agent is the dictator agent and kappa is also 0, then you get back this dictatorial rule. So, affine maximizer in some sense is capturing this the earlier rules, this dictatorial rule and allocatively efficient rule shows up in certain cases.
So, what is the reason for having this kappa function? I mean, I can understand why lambda is used, it is some sort of priority of agents.
So,
what is kappa?
Yeah, so priority of the agent, so you are giving weights on agents,
Yes.
and this is maybe the mechanism design is pushing for certain outcomes. So maybe the planner also wants certain outcomes to be more preferred by the society. Right? It's just a rule. I mean, I'm not going to defend it or criticize it. It's just another rule. The mathematical reason behind this is when we try to characterize all truthful mechanisms, DSIC mechanisms, under certain conditions, they turn out to be an affine maximizer rule. But that's a long story. But this is, at this point, you can just imagine that you are pushing the agents differently. Here, you are pushing the alternatives differently or the outcomes differently.
If I take kappa to be 0 for all allocation and extremely high for just
One specific, yeah. So
then
that
it's going to ignore all the valuations.
yes, yes. Okay. The other one that I was talking about, so just in principle markedly opposite to what utilitarian rule is doing. It is trying to look at the aggregate, the sum of the utilities, sum of the valuations of all the agents. Somebody could be very rich, somebody can be very poor under this rule. So here it is trying to maximize the poorest person, make the poorest person happiest. So it is trying to find out, so for any, so think about this from inside out. So I pick a specific allocation, I look at who is the minimum, so who is actually suffering the most. I pick that alternative which maximizes that minimum. So very naturally this is also called the egalitarian rule. Okay. So these are some example of allocation rules. We will see that do there exist payments where we can actually implement these things. So by implementation, and that is the objective of mechanism design with transfers, can we have good payment mechanisms or payment rules such that in some equilibrium, maybe a dominant strategy equilibrium or in DSIC or BIC, we can satisfy these objectives. Okay. So that's where we are heading. Just to finish the discussion about the payment rules, we have different payment rules. So the no deficit is saying that your sum of the payments, so the mechanism designer is collecting this much amount of money, that cannot be negative. If that is negative, that means the mechanism designer is pumping money into the system so they is subsidizing it, but that's not, so or running into some deficit. So that is not a desirable thing. So no deficit is a desirable thing. So the no subsidy part says that none of the agents will be paid back. So they will always pay to the mechanism designer, nobody will be subsidized. So you can also ask some of the questions about this the payments, that my objective could also be as a planner to maximize this the revenue, right. So this is something like the revenue that I am generating. So suppose I am selling an piece of art. Why should the mechanism designer only be interested in allocating it to the most valuable person? Might also try to maximize the revenue earned from it. This is something that we will discuss tomorrow, not today. Okay. Yeah, so those are very valid questions. The other property of a payment rule, type of payment rule, is where we call it budget balanced. That means you can actually accept money from someone and also subsidize, but on aggregate it is exactly equal to 0. That is, the mechanism designer is not pulling any money, it is not retaining money, it is just in order to do this allocation, it is charging someone and paying that money back to somebody else. So there is no net build up of revenue to the mechanism designer. And this is just the same definition of DSIC that we have looked at just now, said in terms of the valuation and payment. So notice that I have just written the utility. Earlier I was writing the utility in terms of only the f, but now I have two components of that f, which is now the capital F. One component of my utility, which is the valuation component, is affected by only the allocation decision. So this f, remember that f is only affecting your allocation, and your valuation is a function of that allocation and your own type, right. So just in case, so Vi is a function of a cross capital theta I to the set of real numbers. So, my valuation is what allocation I do. So, maybe I give the painting to someone, somebody. If it is me, then I get a certain valuation. If it is not me, then I possibly get 0. So, that is affecting the first part, and the payment that is being charged to me. So, this is also Pi is also a function of the entire theta to this real number, because payment can be dependent on everybody else's type, and we have seen one example where the payment is not a function of that agent's type. Okay. Anyway, so this is just rephrasing the DSIC in the setup that we have discussed. So, we have just set up. So, we just made this comment that what does dominant strategy incentive compatibility mean? It is saying that truth telling, that is reporting your type, this theta i's, in a truthful manner is a weakly dominant strategy equilibrium. So, we have not said what is weakly dominant, because I have always written only weakly dominant strategy equilibrium. There is a stronger version, but let us not spend time on that. But the whole point is that when you are reporting your theta i's truthfully, that is going to be a dominant strategy equilibrium, and that is exactly what is happening here. That if you report your theta I, so this, remember that the second component is the true type, and if you report your type truthfully, then this is the utility that you get, the left hand side. Contrast that your true type is theta I, but you are reporting theta I prime, then that utility cannot be larger than the utility when you are reporting it truthfully. And if this inequality holds for all theta I, theta minus I tilde, theta I prime, theta I, and for all agents, we are saying that this is DSIC, which is saying that truth telling is a weakly dominant strategy equilibrium. Yeah, this is a lot of words. It is just saying that here we will be mostly focusing on the allocation problem, because our objective is to get the object. Let us say even in the example that we have given, I want to give the object to the agent whom values it the most. Do there exist any payment rule which can actually ensure that their truth telling will be a weakly dominant strategy equilibrium? Any payment rule will work, and we will see that there exists a class of payment rules which can actually satisfy this. We will say, and every time we will only say that this f, the allocation component of this social choice function, allocation component is implementable in dominant strategies by some payment rule. We will design that payment rule, but that will not be the focus. The focus will be that f. Right. So, this is the same thing that I just said. Yeah. So, the question here is that what needs to be satisfied when we have a DSIC mechanism. I think I have just written it down for an example. It is just writing that down for a very specific example when there are two agents and their types are either high or low. So, maybe they value it high or value that item as low, and depending on that the inequality. So, essentially explaining or writing this down, it will give you some sort of a feeling what needs to be satisfied. I will not spend time on this. In the tutorials we can discuss this, but this is just for. So, if you have this setup, you write down the conditions of dominant strategy incentive compatibility, that is the exercise, and this is just an example. You have to satisfy it for both the players and for both their types, right. So, if they are highly valued, then they should reveal it highly. If they are low valued, they should also reveal it low. Okay, so, now the properties of the payment is that I need to satisfy that f comma p, which is the complete mechanism. So, this is a kind of my recipe. My allocation function is given by f, which is my desirable objective, and I have a payment scheme. This together is incentive compatible or dominant strategy incentive compatible. This is equivalent to say that p implements f. Yeah, so that's the type of thing that we are going to use. Yeah, so this part is not really very useful. We can again come back. Maybe you can take a note of the slides that we are skipping in the tutorial session, because these are not super important for the story that we are going to do. One other observation is that if you have two different so you have the same allocation in two different type profiles. So this is a property of the dominant strategy incentive compatibility. Maybe you can just try to do it in the lunch or maybe during the before the tutorial session. So suppose you are an agent who is thinking about, let us say I will try to misreport theta I tilde, and but it happens to be such that even if you misreport, the outcome does not change, or the allocation does not change. That is, this outcome, even after you manipulating, you cannot change it. Then it should be the case the payment should also be the same, and it is very easy to see why it is true, because if this was not true, then one of these two things will be more desirable. Wherever you get less payment, you will actually try to misreport there. So DSIC actually necessarily satisfy the condition that if you are by misreporting, if you cannot change your outcome, your payment cannot change in the transfer domain. Okay, so let us get into the so that is one objective. Our objective is to satisfy truthfulness. Now we are getting into another. So that alone is not sufficient. I mean, of course, we can satisfy truthful mechanisms, and we will see some examples, but we also want some desirable properties. So the mechanism design discusses about various desirable properties, and we want to see whether we can satisfy all of them. Until we hit a point where we cannot satisfy all of them, then we try to sort of either take approximate routes or take one property satisfied in full, the other properties in some approximate sense, and so on. So one of the second desirable property that we want to satisfy is, suppose I get in a dominant strategy incentive compatible way two different outcomes, right. So some A as well as some A prime, both are satisfiable, and there exist some payments which satisfy that as well. I will have to choose between one of the two things. Now, if I actually have a Pareto dominated, so what is Pareto dominance? So before we get into the math, let us try to understand it in this way. So suppose I have two different outcomes, and in one outcome each of these players are getting weakly better off, their utilities are getting weakly better off, they are getting as the original one, or someone is strictly getting better off. Then I will definitely prefer the second one, because I want to make everybody happier. So people will prefer that particular outcome, because that outcome is making everybody weakly happier, at least one person strictly happier. That is exactly the idea of Pareto optimality. It also shows up in the cases where we do not use money, that there is no monetary component associated, but because we have money, we are going to say that a mechanism, this f and this p function, is Pareto optimal if at any type profile there does not exist any other allocation, and let us not worry about the payments part for now. So there does not exist any b which is not the same as the original outcome. You have and you also have some payments without this guarantee. Suppose this thing is true, right. So this is a kind of a negative definition. So it is saying that there does not exist any such b and pi 1 to pi n such that everybody can be weakly better off, and the inequality being strict for some I in n. Okay. So this inequality is satisfied for all n. Let us say some j, it is strict. Can we actually have, if I do not have, so at this point do not look at this part, can we actually have any mechanism to be Pareto optimal in that case? In other words, the question is, can we always come up with some b and pi such that this you give me any f and p, I will always beat and find a Pareto improvement on that. So what is this mechanism saying? Mechanism saying is that it is saying that I choose a specific outcome, an allocation given by this f, and I am also charging some payment functions which is also functions of theta. Now, can I find some other outcome and some other set of payments such that this inequality is getting satisfied for all of them and strict for some agent? So, remember that this pi I, so we have not, so we have only said this pi i's and p i's belongs to the set of real numbers, right, not necessarily non-negative real numbers. It can be positive, it can be negative. Positive pi I means that you are charging the agent, you are asking the agents to pay. Negative means you are paying the agents. So, that was a hint how you can actually violate this condition if I do not put any restriction on this pi i's.
So, you can have the same allocation.
You can have a same allocation, okay. So, B is same as f.
And then pi is equal to minus of pi.
Very good. So, everybody sees this point, you can subsidize. So, the mechanism designer can reap itself off and give so much money to other people, to the players, such that their utility is really very large. So, we need, so to make this definition meaningful, we need some restriction on the payments. I cannot really say that my mechanism is Pareto optimal, because you can infinitely subsidize people. It has to satisfy now this condition, that it has to burn or at least gain me the same amount of revenue that I was getting in the original mechanism. So, these PIs are all the amount of money that you have accumulated from this original mechanism. I have to accumulate at least that or more, yet it is going to be better for all the agents, right. So, that makes sense. I am not using any additional money, I am not subsidizing beyond what has already been subsidized, yet I am making things better for all the agents. So, therefore, it is not Pareto optimal. No, so this is PIs are payments from the agents to the mechanism designer. So, it is like saying that I am at least recovering this much amount of money from running this auction. So, yeah, so think about this pi i's as the money that is that the mechanism designer is getting from this scheme, from this running this mechanism. If it is from the mechanism designer, so the minus of pi is the subsidy that is going to the agents. So, I at least recover that much amount of money, still I do better. So, that particular condition is important. Now, why are we bringing in this? So, this is definitely a desirable property. We will see a very crucial connection with this Pareto optimality or something. So, Pareto optimal or Pareto efficient, they are the same thing. In some books you will find this terminology or the other. So, this Pareto optimal and allocatively efficient are one and the same. So, this is something that we have we are going to see. Actually, it is very simple. We will discuss, if I will go a little faster here, but if there are any questions, we can go over this again in the tutorial. So, Pareto optimality, remember that Pareto optimality has two components, both this allocation and the payment. So, I am saying that this mechanism is completely given by the allocation as well as the payment, and it is putting constraints on both of them. So, it is also saying that you cannot do better by at least recovering that much amount of money, and this inequality should get satisfied. Allocatively efficient does not look at the payments at all. So, remember that. So, you do not have this payment component, even though the mechanism remains the same. So, it is making our life much easier. If we have this, then we can only look at allocatively efficient mechanisms, which we were doing so far. It will also be Pareto optimal. Any P that satisfies that allocative efficiency, or at least P is not relevant for allocative efficiency, I can only look at F, and that will be Pareto optimal as well. So, okay, so let us do the do this implication. First, the easier direction. So, if it is allocatively efficient, then it is Pareto optimal. We will do it in the other way. If it is not Pareto optimal, then it is not allocatively efficient. and this is very easy to see. So, not Pareto optimal means that so you have this inequality for all and one agent has a strict so this is only the payment thing. So, this is so the not of that condition is that there exists some b, some pi and some theta, such that this even though you extract the same amount of payment, this inequality will get satisfied for all agent and strict for some j. Right? And what do you do? Then very next step? No, we will have to show that that is not allocatively efficient. So, what will be my counter example to that allocative efficiency?
There exists a mechanism that is increasing the total utility.
So let us remember what was allocatively efficient. So, allocative efficiency meant that I have allocative efficiency meant that if you have f theta, that is an argmax of the sum of the theta i's, right. I think I have so I have used the valuation here. So, let us write it in that way. So, v I of a comma theta I for all the agents and I in n, and you pick a from the set of allocations. So, this is your allocatively efficient one. So, if it is not allocatively efficient, that means there exist. So, I say that let us say some a is not allocatively efficient. That means there exists some b, right, which can actually beat this. So, the sum of the valuations that you get under this a will be strictly less than the sum of the valuations that you get under b. Okay. So, my question is, what is my this candidate b? I will have to come up, if I want to show that this is not allocatively efficient, I will have to come up with some b which will beat it. So, can I use the same b?
Yes, because you will have n inequalities, you can take the summation.
Okay.
And there would be some one inequality which has a strict inequality, so that side would be greater than this. So
You will also have to use this fact because pi i's. So just remember that you will have to also use this factor, that this is at least as much, but everything falls in place. You just see that the sum of the valuations of all the agents minus the sum of the valuations under the original mechanism, which was your f mechanism, that is going to be strictly larger than 0. So, clearly this is not allocatively efficient. So, clearly if it is not Pareto optimal, then it is not allocatively efficient. So, we have proved the reverse direction. Now, the forward direction, forward direction will also be proved in this way, but this will be a constructive proof. So, we have an allocative efficiency which is just saying that I have this mechanism f comma p and that is not allocatively efficient. That means this there exists some b where this b is strictly larger than that. Now, I will have to construct a different pi using the fact that I already have that p1 to pn functions. How can I actually construct that such that when put them together, it will actually violate the condition of Pareto optimality. So, here is the construction. The delta is just looking at the difference. So, because I know that it is not allocatively efficient, this is strictly larger. So, this difference I am defining as the delta, and I am constructing my payment, new payment, which I will use for showing that it is not Pareto optimal, is for every agent that valuation at this new b minus the valuation at the original mechanism plus the original payment that was given by the mechanism minus delta by n. So, there is a reason why I have chosen it. So, what exactly is the sum of pi I? Because I will also, so remember that for Pareto optimality I have to satisfy that the sum of the pi i's is at least extracting the same amount of payment from the original one.
it's equal to the summation of pi i's.
Summation of pi I is
equal to summation of pi, sir.
Summation of pi's, because this term I have defined it in that way. So, this will be minus delta, and this sum when you have it, that is exactly equal to delta. So, that will cancel out, you will have this part. So, at least from the if condition of that Pareto optimality, everything is in place. Now, why is it strict? Because that is how we have constructed it, right. So, you just take these numbers on the other side. So, the utility of this agent in V I minus P I at that allocation and that payment that we have constructed, minus the utility in the original mechanism that is strictly larger than 0. In fact, it is for every agent this is positive. So, clearly this is not a Pareto optimal, because you have a outcome and a payment pair which can make everybody strictly better off. Okay. So, yeah, and also this we have observed. Okay. So, allocatively efficient and Pareto optimality are same, that gives us a relief, because now we can only focus on allocative efficiency, and in the rest of today we will look at the different types of payment schemes which can actually ensure us allocative efficiency. Any questions? How much time do I have? 30 minutes. Okay. Okay. Okay, so let us start with the first payment scheme. It is a little I would say unusual and not quite where we want to get to, but this is a little general class, and we will later fix this particular payment rule into a very specific rule which satisfies many other properties. Okay, so what is this payment rule? So, this is called the Groves payment rule, named after Groves, who has actually proposed it. So, now our whole focus is to ensure that we have a payment scheme which implements this allocatively efficient social choice function. We have already motivated why allocative efficiency is good. I want to ensure that people report their true types in a dominant strategy by choosing certain payment scheme, and this is one specific thing, and we want to see why this particular structure is important. Okay, so what is this payment scheme? So, you look at the types that has been reported. So, you can think of this as the reported types, not necessarily their true types, it can be anything. There are two components. The first component can be any arbitrary function, just the restriction is it cannot be a function of the agent's type, right. So, this is not a function of theta I, it can be any arbitrary function, can be a constant, can be any arbitrary function of theta minus I. And the second part is, once you have solved this allocative efficiency problem. So, this is happening in two stages. First, you solve this allocative efficiency problem, in some sense you are solving that argmax problem, you get that allocative efficient outcome, and you are looking at all the agents. So, when you are calculating the payment of agent I, in the second part you are looking at what is the sum of the valuations of all the agents except agent I. Okay. So, think about in the I think I have an example. Okay, so let us look at this, walk you through, then we will understand this better. So, our example is the single indivisible item allocation, what we have started with. Now, we have 4 bidders, 4 agents. Suppose their types or their reported types are this 4 numbers. So, if they have reported it, what is the allocatively efficient outcome? So, single indivisible item. So, that means the allocation can be like those A1 to AN, where each of these things can be either 0 or 1, and sum should be less than equal to 1. That means you give the item to exactly one agent, at most one agent, can even not sell that item. 1 0 0 0, that means you give the item to agent 1, and that is allocatively efficient because you are maximizing the sum of the valuation. So, here the valuation is just theta 1 times A 1, right. So, and then sum over all those things. Okay, so, let us fix. So, okay, so we appreciate now that what is the allocatively efficient. So, we should give the item to agent 1. So, h I theta minus y is suppose the minimum of all this theta minus i's, right. So, it could be any function, I am just choosing this min. And if you if these are the reported values, then you can just work it out. The minimum will be 4, 4, 4 and 6 for this. Now, what will be the payment? So the efficient allocation gives the item to agent 1. So, how do we calculate P1? Let us now go back here. So, H1 under this case was 4. So, that is the first term. Notice that because this item went to agent 1, the sum of the valuation of the other agents is 0, because they are not getting the item. This allocation is giving the item to agent 1. So, for agent 1, when we are going to calculate the second component of the payment, that will be 0. Everyone sees this? So, this part will be 0. So, therefore, player 1 will make some payment. So, this is the convention that whatever is, whenever it is positive, that means this player 1 is paying to the auctioneer or the mechanism designer, while for player 2, let us look at this. So, now it will be H2, and H2 we have calculated as 4, but minus what should be this sum when we are looking at I equal to 2. We are summing over the valuations of all the agents except agent 2. It should be 10 because the item is going to agent 1 and that agent's valuation is 10 when he gets this item, right. And similarly, you can see that it will be, that second term will be 10 for all the other cases, because if 3 or 4 or 2 is not included in the sum, then the valuation is actually the valuation of agent 1, which is 10. So, the second component is the same, just that the first component is how we have defined it. Okay. It is a strange mechanism because it is just collecting 4 amount of money and giving out 6, 6 and 4, right. So, it is actually running into a loss. We will fix this, but just to keep you informed ahead of time, this indeed is a DSIC mechanism. So, we will show this. You can choose any HI theta minus I, and later on when we go to the next mechanism, which is a more popular mechanism, satisfies many other properties, where there we will fix this HI theta minus I. The only variable component here is this HI theta minus I, but if you choose any such function, it will work, but that will not satisfy some of the properties. And in particular, what is this property? Do you remember the sum, the properties of the payments? The sum is, if it is less than, so this mechanism is running into a deficit because the sum of the payments here is negative. Okay. So, we do not want a deficit mechanism, we want something which makes some profit, and that is why this mechanism, this particular mechanism is not a very interesting mechanism. Okay. So, our claim is that this gross mechanism. So, what is the gross mechanism? It has two components. The first component is this F component, which is the allocatively efficient. So, if I look at Groves, it is fixing two things. So, the F is same as the F allocatively efficient, and the payments are given by let us say PG, what we have used, right. So, yes, we have used this P superscript G for Groves. So, that is being fixed, and we are claiming that this F AE comma this PG, this particular scheme is DSIC. Okay. Okay. So, why is it DSIC? And this is just one way implication that we will have to show that this is DSIC. Do you see, if you write down the expressions for payments and the allocations? So, note that. So, you see that so there are two things that we will have to consider when we are talking about DSIC. One is when this agent is truthfully revealing and other agents can report whatever they want to. Suppose under that condition the outcome is A, right, and suppose by changing its type it can get to something else. The other case is easy, where even if you change and you do not change your outcome, from that exercise that we did, we know that the payment should also be the same, payment should remain the same. In that case, this inequality gets satisfied with an equality. That is an exercise, but I am not considering that. So, assuming that agent I by misreporting changes the outcome. Now, this is not going to be beneficial for that agent. Why? So, first notice that the way we have defined allocative efficiency, right. So, if I have, so agent I's true valuation is, so it has reported theta I, and because of that the mechanism designer has actually maximized this term, right. So, other agents have reported theta tildes, and that agent has reported theta I. So, this sum is going to be by definition, because it is maximizing that the sum of the valuations, this will be larger than any other B, right. So, any other allocation in set A, in particular I want to put B here, right. Okay, so, if this is true, now let us read this one by one. So, we have to show that the left hand side, when he is reporting truthfully and this is the payment given by the Groves, that should be at least as much as when he is misreporting to theta I prime, and when he is so the payment is also determined by that. So, let us expand this. So, we know that what is this P I. So, this will be P I G, which is the gross payment, and if you write this down, the way we have, so this is the trick here. We have used that j not equal to I, and the allocation is still the allocation when he is reporting it truthfully. So, this term and this term you can club together, right. So, this is exactly the V I of A, right, and this term is the same A, because that is what you get when your outcome is A. So, there is nothing, I mean this is just a set of steps that you will have to follow. So, this term, and notice that this function is not dependent on theta I at all. So, the agent I has no role to play, this will be a constant term on both sides of the inequality, and because this term is what we have just shown, that this is greater than or equal to B, which happens to be that when this agent is misreporting, right, and then you unravel that again, make this as your payment. So, notice that this is the payment that you get when you misreport to theta I prime. So, this part is the payment, this part is the allocation when you misreport, and this because of this inequality you get back the stuff. It is kind of a very regulation thing, just have to stare it for a minute, maybe spend one minute for this one. Okay, so, gross payment, even though that has a very strange term here, it is DSIC, and it satisfies one of the very desirable property, which is allocatively efficient, which also says that it is Pareto optimal as well. Okay, but as we said that for certain choices of HI, it's running into deficit, and it might not always ask people to pay. Those kind of things will not get satisfied. So, therefore, we need something better than this. Okay. Any questions about this? So, the improvement that we will do over this gross payment is to fix that particular function here. Okay. So, and this is also a little maybe scary in the beginning, but it is not that scary, because you are just changing this HI theta minus I, assuming that the agent I never existed. Okay. So, suppose I have the same set of allocations that is available, and if I pick the allocation from the set of allocations which maximizes the sum of the valuations when agent I is not at all present. So, imagine that this is a world where I have actually removed agent I altogether, and I have tried to maximize the sum of the valuations. The second term is inherited from the Groves mechanism. So, that does not change at all. Now, this particular thing, which is a special case of the Groves payment rule, is going to be the Vickery-Clark-Groves mechanism, named after 3 different individuals, Vickery, Clark and Groves, so named VCG. It is also known as pivotal mechanism, So, you can think about this payment as the sum value of the other agents when you are looking at this first term where it is in absence of agent I, and the second one in presence of agent I, but that the sum is taken with respect to all the other agents. In some sense, this is actually the marginal damage that you are doing to the other agents. Because of your presence, maybe some of the agents could not get much good items. So, you are actually reducing their valuation. If you are not present, maybe they are getting more, and that difference you are asked to pay. That is another way of interpreting this. Now, why is this interesting? I mean, of course, this is a special case of Grove's mechanism. So, it will automatically satisfy the GSIC condition. So, there is no nothing new to be shown, right. Yeah, but there are certain additional properties which was not possible to do for any arbitrary HI now gets satisfied for the VCG mechanism. Okay, so, this is the utility under that. Now, you can notice that when you have, of course, under certain, so if you have all the agents which are having goods, we will get back to this later, but you can, I mean, one of the important property is of individual rationality, which says that if you participate in this game, you are never going to lose money. So, it will never happen that you are not given that object, any object, and you are asked to pay something. That will never happen under VCG. You are always going to be charged less than what you value. So, this difference will always be non-negative, of course, under certain conditions. Yeah, so these are the conditions. I mean, we can discuss about this either offline or in the tutorial, but it is not so important. It satisfies many other properties. Okay, so now let us get back to this original single object allocation. So, now we can think about this single object allocation as our problem of, so we are trying to maximize the allocative efficiency, and what is the payment rule if we apply VCG. So, think about from the viewpoint of somebody who is not the highest bidder, right. So, if in the efficient allocation that agent is not the winner, single object allocation. So, what will be the second part of this sum? We have just done this, right. Value of the highest bidder. So, let us say that is k, some number. When this agent is not at all present, this is the first term, who will get that object? Still the same agent, right. So, here I am assuming that I is not the highest bidder. So, if you remove that agent, still the max is the same, and in his presence also he does not win. So, the sum of the valuation is still the same k. So, what will be the payment to the, it will be a 0 for the non-winners. Now, for the winner, now it changes, right. So, if he is present, what is the second term? He is present, but I am summing over other agents. It will be 0 because nobody else is getting the object, their valuations are 0, right. So, the agent who has the highest value, I am just removing that agent in my summation, yet I am looking at the same allocation. So, this is the second term will be 0. What will be the first term? The second highest bid, right. So, this is exactly, so now what is this mechanism? VCG is the second price auction. So, it is a very special case of, so you can now see that even for more general setup, we can actually extract that specific case. So, VCG mechanism gives rise to the second price auction when applied to single object, single indivisible object allocation. Yeah, so this is just an example, I think. The other name for VCG mechanism is also the pivotal mechanism. So, this is a kind of a keyword, should have highlighted. So, why is it pivotal? So, let us say the public goods example. So, suppose there are one football ground, one library and museum that can be made. Agent A does not value football at all, library or museum has these values, and there does not need to be, I mean these numbers are not normalized, you do not need to be need to add them to the same number for all the agents. B likes this one more and this way. Okay. Now, the VCG mechanism first chooses the allocative efficient allocation, right. So, allocatively efficient outcome. So, which one is the allocatively efficient outcome? So, you will just have to look at the outcome and sum it up, whichever maximizes, that is my allocatively efficient outcome. C, I think, right? Yeah, okay. Museum, okay. So, the last outcome is the maximum, maximizes the social welfare. Okay. So, now let us, so that is the outcome. Now, we will have to decide what is the payment. Okay. Let us, there are calculations, but let us say what is the payment, right. So, I will have to calculate it for A. So, if I remove A, so the first component of the VCG scheme is that you do not look at, so you remove the agent altogether and recalculate the same thing again. Outcome might change, and that will change the sum of the valuations of the other agents. So, what will be the outcome if A is completely removed? Football, because this sum is larger. So, that is giving you 105, right. So, that the first term, yeah. So, this first term will be 105, and when we have taken the allocatively efficient outcome, what was the sum of the valuations of the other two agents when I am removing A? 100. So, what will be the payment that A should make? Should make payment of 5. Next, I remove B. So, I am going to calculate the payment for agent B, remove that guy. So, what becomes the outcome now? Now, it becomes library, and that gives 70 plus 50, 120, and when it was the same efficient outcome, the sum of this. So, now agent B I am not looking at. So, the sum of these two things is 100. So, what should the agent 2? Yeah, so it will pay 20. Yeah, so 120 minus 100. Right. So, notice one thing, that whenever I have removed A or B, I have actually changed the outcome, right. So, those kind of agents are called pivotal agents, because of their presence the outcome has actually changed. If agent B was not there, the society was very happy building a library. Because of his presence, museum was built. So, that kind of an agent is a pivotal agent. So, if A was not there, we would have built a football ground. Because of his presence, we are building a museum. So, those are pivotal. So, what about C? If I remove C, what is the outcome? Museum, and in his presence, museum. So, he is a non-pivotal agent. So, what is the payment for this agent? So, non-pivotal agents are not going to pay anything in this mechanism. So, that is exactly the point. So, it is a non-pivotal agent. So, that is why when he is present or not present does not really matter. So, therefore, the VCG will not charge him. It is like you are just an extra, you do not have such a high preference such that I will actually change my outcome. So, therefore, you are never taxed. So, this is sometimes also a desirable property. And yeah, so why this B is paying a little larger amount? Because so when he is not there, the utility is very high, and he is actually making a lot of damage by showing up in this mechanism. So, that is why he is taxed more than other agents. So, this is exactly the reason why it is also called pivotal. Only the agents who are pivotal, whose presence changes the outcome, are asked to pay anything. Non-pivotal agents will never make any payments. Okay. So, another example of allocation is when we have not just one object to select, but a multiple set of objects, and we can actually give a combination of objects. So, in this example, suppose there are two items, and the allocations could be something like the bundles could be something like empty bundle, for which everybody has a 0 value. It could be just the first item, just the second item, or the bundle 1 and 2 together. And this numbers should not does not necessarily add up. You can see this, that when I get two different items, they might not add up to their individual sums. It can, but this is more general setup. You can calculate this. I think this is a very simple exercise. I don't want to spend time on that. You can look at those setups. Okay, so yeah, so therefore, in the combinatorial setup, I think I'm mostly done with the VCG part. You can actually extend that example when we have m different objects and you have a valuation which is defined over all the sigma to the real numbers, and you can apply VCG mechanism. How we will find the efficient allocation, that's a good computational question. I am not getting into that because it might take another long discussion. In certain cases, this type of problems are, so finding that FAE is not easy for combinatorial allocations. So therefore, if that is computationally hard, then you cannot actually use VCG, because VCG requires you to calculate the efficient, the allocative efficient allocation. If you pick something else, then that same payment of VCG will not ensure truthfulness anymore, because it's everything is sort of on the razor's edge. Anything different from the allocative efficiency will differ, but there are results where if you approximately maximize the utility, then you can actually come up with a different payment scheme, and that is exactly the whole idea of mechanism design, that you can try to find a different kind of a payment scheme such that even under that approximate social welfare maximization, you can still get the truthfulness guarantees. So, in the allocation of goods, so the VCG payments, as I was saying, that VCG mechanism has a bunch of nice properties. One of these properties, that if an agent does not get any object in the combinatorial allocation, that agent will not pay anything. Okay. Let me start individual rationality after the break. Let me just stop here and